Welcome to Ask and Learn.
For this problem, we have a concrete dam with on its backside facing the water, or adjacent to water, we have a parabolic cross section as follows. For the first part of the problem, we're asked to find the resultant of the reaction forces exerted by the ground on the dam. The dimensions of the dam are as follows. It's 4 meters high. The rectangular portion before the parabolic curve is 1.5 meters wide, and the parabolic curve spans laterally 2 meters into the water. The depth of the water is 3 meters. Now, this problem is in units, is in SI units, so our density of water will use 1,000 kilograms per cubic meter. Density of concrete is 2.4 times 10 to the third kilograms per cubic meter. And they ask us to calculate this for a 1 meter thick cross section of the dam. That would be 1 meter into the plane of the page. So for the first part, part A, where we're finding the resultant of the reaction forces, I elect first to calculate the lateral force of the water, and this is before the parabolic curve. The lateral force of the water as it presses against the dam. And I'm calling that vector P sub W for the force of water. We use the equation for water as it presses laterally the deeper it goes, and that is this B times the volume density of water times the height, and that's this equation here, and we need to integrate that equation over the infinitesimal, or multiply it by the infinitesimal dh and integrate it by the variable h. Doing that, we're left with the product B times the volume density of water times the height squared over 2, and we're evaluating from 0 to 3. Plugging all the numbers in for that as follows, we are left with 4.5 times 10 to the third kilograms, and that is again, the lateral force of water pressing against the dam. We can note that since this equation forms a line, the force profile will be triangular in shape. And for triangles, the centroid of a triangle is 1/3 up from the base. If we're calling the base this leg of the triangle here. So our location of the force vector at the centroid will be 1/3 the height of the water. Water height is 3 meters, and that leaves us with the centroid of the lateral force located at 1 meter from the ground, or the ground of the dam. Next, we will calculate the weight of the rectangular portion of the concrete. And that's simply base times height, a base of 1.5 meters, a height of 4 meters, and a thickness of 1 meter, times the density of concrete, which is 2.4 times 10 to the third kilograms per cubic meter. That leaves us with 14.4 times 10 to the third kilograms. The centroid of a rectangle is half of its width, and and that would be the half of the base. We're calling the base now because we're looking for the x location of the centroid. And dividing 1.5 meters by 2, we get 0.75 meters. Next, we'll calculate the weight of the parabolic spandrel. That's the part that spans from our rectangular division line here to point B. For a parabolic spandrel, the weight follows this equation here. It's 1/3 of the what would you call this? The span A times the height. So we have a 1/3 coefficient here. We have a 3-meter height and we have a 2-meter span. Again, that span is from our division line here from the rectangle to point B, which is 2 meters, multiplied by the 1-meter depth, and the volume density of concrete leaves us with 4.8 times 10 to the third kilograms for that portion of concrete. To find the x location of the centroid here, we look up its formula for a parabolic spandrel and subtract it by the total span here of, I believe it's of 2 meters. So that leaves us with the formula of its location of A, the span of 2 meters, minus 3 times A, again 2 meters, that product divided by 4. And then we have plus the total offset of the section, which is 1.5 meters from A. Plugging those in, we find 1/4 times 2 meters plus 1.5 meters is 2 meters. Again, that's the x location of the centroid of this parabolic spandrel. Finally, we need to calculate the weight and centroid of our parabolic shaped section of water, and that's from point A, that spans from the edge of the rectangular boundary to point B. For parabolic area, our weight can be calculated as 2/3 the span, horizontal span, times the height. Plugging those numbers in, we're left with 4.0 times 10 to the third kilograms. And now finding the x location of that centroid, the formula is 3/8 times the total length of the span A, the horizontal span, and we're going to subtract that value from the full length of A because we're looking for the opposite side. And we're going to add the total offset as well. In this case, the total offset is again, the beginning of the rectangular boundary, I believe. Yeah, 1.5 meters. So plugging in these numbers, we're left with 5/8 times 2 meters plus 1.5 meters equals 2.75 meters. Now that we have all the weights and their relevant centroids, we can sum the force components and sum the torques about point A in order to find the resultant forces. And I've sort of denoted them here. We have a lateral force that arrow here that's going, and that's we're calling vector H. It's going to be equal and opposite to the vector P. And then we have a vertical vector V that's going to be equal and opposite to the sum of the total weights of W1, W2, W3. Summing the opposing lateral forces first, we find that H must equal 4.5 times 9.8. This 9.8 is the acceleration due to gravity, which converts our kilograms into newtons, times 10 to the third, which is the volume density of water. We're left with 44.1 kilonewtons in the rightward going direction. That is our horizontal force H. Now to sum our vertical linear forces, we sum up each of we sum up the kilogram weights of the three sections calculated above, multiply them by the acceleration due to gravity, and then by the volume density of water. We're left with 227.4 kilonewtons in the upward direction. Again, these are reaction forces, so they're going to be equal and opposite to the forces exerted on the ground. And next, we'll calculate the torques. This, we have the moment arm of each, and we want to make sure all of the torques going in the which direction? I believe the counterclockwise direction we'll call positive, and all the torques exerting, no, other way around. All the torques being exerted in the clockwise direction we'll call positive. Torques exerted in the counterclockwise we'll call negative. From above, we have a moment arm of 0.75 times 14.4 kilograms for the torque exerted by one section. The next section, we have 2.0 meters times 4.8 kilograms. The next section, we have 2.75 meters at 4.0 kilograms. All these torques go in the same direction here, but now that will be clockwise direction. An opposing torque to those is that due to the lateral force at 1 meter. Vertical, keep going down here, 1 meter vertical, and at 4.5 kilograms. And then we have this entire quantity we're going to multiply by the acceleration due to gravity, and this volume density of water, which gives us, I'm sorry, this isn't volume density of water. This is simply a factor that I factored out for each of these. Since we all have units of thousands of kilograms, I've factored that out. We already considered density of water in our earlier calculations, so please note that error on my part. That is going to leave us with units of kilonewtons. And multiplying these out, we get 263.6 Newton meters for our total torque. With that, we can then determine the point of application of that resultant force, and that's simply the absolute value of the reaction force of the torque at point A divided by the total vertical force exerted by the ground. That turns out to be 263.6 Newton meters divided by 227.4 newtons, leaves us with units of meters as 1.159 meters to the right of point A. That is the location of our point of application. So we need to box that. And I'm sorry, let's do a better job of that. Okay, and we need to box up an answer here, up here as well. We have 227. That is an answer that shows up in the back of the book. And we have 44.1 kilonewtons in the rightward direction. That's one of the answers they requested as well. And finally, we can answer part C. We want to find the resultant of the water pressure. So to do that, we need to note that the water pressure, the opposite of the resultant, will be the combined vector sum of the weight for our, we're calling W3 of our third parabolic section of water, plus the lateral force of water, which is in the leftward going horizontal direction. So we're going to get a vector sum that is going to span, its angle is going to be in between those two vectors. Adding these vectors together, we have 4.0 times 9.8 kilonewtons in the y direction for W3, which turns out to be negative 39.2 kilonewtons in the y direction. For our lateral force vector, we have negative 4.5 times 9.8 kilonewtons in the that should be the x direction, minus, and let me get that real quick, and that product comes out to 44.1 kilonewton. I'm sorry, negative 44.1 kilonewtons in the x direction. Make that fix here. This should be please. It should be x. Okay. So we can calculate both the magnitude and angle of that vector sum. Writing out the vector in full here. Then taking the magnitude, which is going to be the square of this component, the square of this component added together, and then the square root of the sum of those two squares, leaves us with a magnitude of 59.0 kilonewtons. And that vector will have an angle of the, in this case, I'm going to take an arc sine. That's 39.2 for our distant leg of our right triangle over the hypotenuse of 59.0. We take that quotient and take the arc sine of it. That leaves us with 41.6 degrees. That will be the angle that the water exerts, and or the resultant of the water, and it will be in this direction, negative 41 degrees from horizontal. This is another boxed answer. Let me do that. And that should conclude our problem.